So I'm very happy to be here among old colleagues, and thanks for accepting. And very happy to be here. Yeah. So basically, I will just present the recent work that I've been doing in IIT Bombay. So I have this experimental active and living matter group. So at the outset, I'll mention that this work is done by my PhD student Somnath Paramanik, and we have been working in close collaboration with our theory colleagues and funding agencies. Um, all right, so I'll maybe save some time by not introducing what active matter is to this audience, but what I'll maybe quickly mention some of the experimental systems that have been studied over many years. And the most interesting feature of this is like we want to mimic what's going on in nature, right? We want to mimic what I call lifelike dynamics. And the underlying feature or the most important aspect here is that all these emerging phenomena, they are like very sensitive to how the microscopic dynamics is and how microscopic constituents are interacting with each other, right? So basically in our lab, so we have introduced another new kind of experimental system, which I term as robotic active matter. And the reason we had to invent a new system was because we wanted a lot more control over the microscopic dynamics, and also in hope that we can tune the interparticle interactions in a much neater way. And in some sense, we are our aim is to like create some kind of all-in-one experimental system. Um, so to this end, I'll quickly show you how my robots look like. So they are about 7.5 centimeter long, and these are some of the components that it has. The most important one being the microcontroller, which we can program according to our will. It has motor drivers and wheels. So once the signal goes from the motor drivers, it drives the wheels, which makes it self-propelled. And it also has hardware components like LDR, light intensity sensors, IR sensors, which we are planning on using to control the interparticle interactions. And this is how it typically looks like. Yeah, so just things that I mentioned. So this is a typical experimental setup. So we have a high-speed camera mounted at the ceiling with a projector to project light, and the robots perform their motion on this white plane. Just to quickly show you what are the basic dynamics of this robot. So very trivial. So if both the wheels are moving with the same speed, so your robot will just go straight. If you give opposite velocity to two wheels, it will just spin. And if the velocity is different on two wheels, it will just do circles, right? So this is how this moves. And this is just a cover that we have put, and these two dots, they help us in tracking the robot. So first thing that we did was to basically model this robot as an active Brownian particle, just like Sanjib mentioned in the last talk. So in this model, there is only one noise source, which is the angular velocity, and eta here is the noise. And if we want to extract such a motion in our robot, we just have to do a little bit tinkering, in the sense our robot is driven by two wheels, right? And we want its center of mass to trace out an active Brownian motion. So therefore, we just write down the robot equations, which are given by this, where VL and VR are the instantaneous left and right wheel velocities. And we can set some constant velocity, which is VL plus VR by 2, and that is your active velocity. And when we just match these two equations, we get the input variables which have to go into the wheels, and that tells you the instantaneous speeds of your wheels in order to get such an active Brownian motion. And here the noise we have picked is basically a uniform distribution from minus eta to plus eta, okay, with equal probability. And these numbers get updated after every epsilon second, which is like millisecond, which we can tune according to any value basically. So I'll quickly show you. Once we do that, this is how a typical ABP motion looks like, something out of textbook essentially. And this is a long time trajectory. And when we do quantifications of this mean square displacement, we see that it shows an excellent fit with the theory, which we do with our collaborators. And we also do things like velocity autocorrelation function and all, which falls exponentially as expected. So the next thing that we wanted to try out was an active Brownian particle with the translational noise. So it's like you have some ambient temperature. Um, in order to do that, so we just basically input two random numbers between some, so with some non-zero mean, which is VA, right? And we just put these values at every instant of time. And here VA will set the active velocity, and the noise will come from these random numbers, right? And when we do that, this is how the typical dynamics look like. So you can see it's still an active Brownian particle, but at very small time scale, it's very noisy, which you can see with this trajectory. So these circles represent the position of the robot at every instant. And you can see that very short times, it does a lot of back and forth motion, which was missing in the ABP, where there was no externally added noise. Colors are just time. Yeah, I forgot to mention. So that it evolves from green to yellow. Um, and that reflects very well with this diffusive motion at the very small time scale due to that noise. It goes ballistic due to the activity, and at very large time again it's just a random diffusive motion. And so this is the fit. This is the theory that we fit with the model. Um, and again, like if you ask me whether we can make it as a Brownian particle, so answer is very simple. So you just set VA equals 0 so that its average speed is 0. And this is how a typical Brownian motion looks like. So it's just, okay, so this is at some light, the feature that I didn't highlight. So it also has an intensity sensor, so we can externally control the magnitude of noise in the system. So basically, we are just jumping between these MST curves. So the yellow one being at very low temperature, low noise, and when I increase the intensity of the light, it becomes a lot more noisier right here. Okay, so I'm almost done. So finally, like another very interesting thing is another very widely used model to understand active systems is what's called run and tumble. And it's seen by these microscopic organisms like E. coli. So rather than just doing random walk in 2D, so they just run in one direction for some time. They get confused. They want to find a new direction where they can find food. So they tumble and find a new direction. And typically, and that also we can actually generate in our robot. So basically, it just
4 minutes.
yeah. So I'm done. Yeah. So it just runs in one direction for some time tau, then tumbles, and then again runs by some time tau. And this tau is picked from an exponential distribution because that's what experiments show us. And when we do that, this is how it typically looks like, right? It's like run and tumble motion. And again, like the same thing, we do mean squared displacement, and it shows tau squared at low time scale due to this ballistic motion. And at large time scale, it's just like a diffusive thing. And the equation that we have used to fit this comes from this paper by Luca Angelini. And there is an interesting parameter here, which is tau t. And this is nothing but the tumble duration, right? So if you think about it, all the physical systems, they have to take some finite amount of time to turn and find a new direction. So it can't tumble instantaneously. And that features here in the model. And that also we can tune in our case. And typically that's how it looks like. So basically I'll just conclude. I don't have any sentences, but I'll just show you these 4 movies. So we have very good control over microscopic dynamics at single particle level. So this is ABP with noise. This is run and tumble and Brownian. And yeah, so I'm done. Thank you.